Welcome to a tutorial on digital electronics, and in this tutorial video we're going to discuss about the you're right, we're going to discuss about the Karnaugh map. Okay, so as you all might be knowing that we can express certain outputs if we require the certain outputs of a digital circuitry or a digital system. Then they can be basically expressed as certain Boolean expressions. Okay, they can be just the outputs of certain digital systems can be expressed in Boolean expressions. Okay, so rather, yeah, that's better. Okay, so now these Boolean expressions that we can derive for each circuit, they need to be reduced. Okay, they need to be reduced to their simplest forms. Okay, they need to be reduced to simplest forms possible. Okay, so simplest possible form. Okay, so now the basic technique in order to reduce a Boolean expression to its simple form is by the use of the laws of Boolean algebra. So we have got the Boolean algebra and its laws to do that. Okay, but the problem with this system is that there are lots of laws in Boolean algebra, and as a result you gotta always keep them stored in your memory for quick usage. And it's not possible for everyone to just go forward and mug up all the laws, and you need sufficient time to become an expert onto as to how you're supposed to apply each law to mathematically reduce the Boolean expressions down to their simplest possible form. So we needed a method, okay, a method that we could basically use repeatedly with time, and that basically anyone with the little knowledge of Boolean algebra could basically do that. So from that's the point where the Karnaugh map was introduced in order to reduce the workload. Okay, so if I just take for example an expression, a Boolean expression. So in that case, we also know that a Boolean expressions can be represented in two forms. Okay, so Boolean expressions can be represented in two canonical forms. So one is the SOP form and the other is the POS form. So an SOP form stands for sum of products, okay, while the POS stands for product of sums. So let's say if we have an expression that would look something like, let's say, a bar b bar plus that of a bar b, and then again we have ab. So now you can see that each of these groups of variables that are just being added up together, these variables are just these groups are just producted together. Okay, they're just, the variables have been just multiplied up together to form a product, and each of these products are just being added up together to make the final expression for a particular digital circuit. And now that's the format of the sum of products expression. So now we have the entire summation of various product groups. Okay, and now each of these groups is just referred to as a minterm whenever it comes to the SOP form of representation of Boolean expressions. But for the POS form, an expression on the other hand would look something like I'm just showing it over here. Okay, there you go. Now you can see in this particular expression that we have certain groups of variables that are basically expressed as certain sums. Okay, and then these sums are taken up together and multiplied together to make up an output expression for a digital circuit. Now this format of representation of an output expression is referred to as the POS format of Boolean expression. Okay, where POS stands for, as I said, product of sums. So we can see that these groups that are just summed up, where the variables are basically summed up together, they are just multiplied again. The individual groups are just basically multiplied again to constitute the final output expression. Okay, now each of these groups, in case of the POS form of representation, is referred to as a max term. Okay, so this is the basic difference between a representation of Boolean expressions. And now whenever we're dealing with them and we need to reduce them, we basically intend on using a K-map, as the method is faster. Okay, so let's say if we have an SOP expression, like I said, so if we have an SOP expression, let's say f that reads something like this: a bar b bar plus that of a bar b then ab, like the one I just illustrated right over here. So if we have just this form of expression over here for a Boolean expression of a digital circuit, and let's say we want to basically reduce it using a Karnaugh map, then first of all what we got to do is that we got to identify how many variables are there at the most. Okay, so now we can see that the entire expression consists of at the most two variables. One is a and the other is b, so we have a maximum of two variables. Okay, so the Karnaugh map that we desire, or rather that is basically required in order to accommodate this particular function, should consist of 2 to the power number of variables. So here the number of variables n is equal to 2. So we shall require a Karnaugh map that will have 2 to the power 2, that is 4 cells. Okay, so you might be not getting the heck of what I'm trying to say, but if you kindly take a look at this particular diagram that I'm just going to show you over here, I'm basically going to draw a Karnaugh map. Okay, so a Karnaugh map, you can basically consider a Karnaugh map as a graphical representation technique of certain combinations of variables in a particular output function. Okay, for any type of digital circuit. So here we have two variables, as I said, a and b. Now this Karnaugh map should consist of 4 cells, so we need to divide it into 2 rows and 2 columns. So there you go. That's 2 columns, and here we have 2 rows. So for the rows we need 1 variable. Let's just take up this variable a to designate the rows. Okay, so I just write it down over here. And for the columns we need another variable, so we have b. So let's just designate the columns with the variable b. Okay, and now as I said, each cell would basically represent a particular minterm. As we can see over here, since this is a SOP format of representation of the output expression of a digital circuit, so we can see that there are various combinations of the minterms that are present over here. So each of these cells basically represent each such combination of a particular minterm. Okay, so let's just designate the rows and columns. So in order to bring that out, as I said, in order to bring the respective combinations of the minterms, we shall designate or rather start designating the rows with binary data like 0 and then 1. Okay, and then the other variable b can also have 2 possible values, that is also 0 and 1. That's right. And now each of these cells need to be numbered. So the first cell over here is going to be numbered as 0, and then we'll have 1, and then again come to the other one, the next row, then we have 2, and then this one will be 3. Okay, so now we can see over here this particular 4-celled Karnaugh map. I mean, this particular figure that we have now over here is basically the Karnaugh map, or we can also call it a K-map in short. So this is basically a 2-variable K-map that I'm just displaying over here. So in this particular K-map, as you can see, as I said, each of the cells would represent a particular combination of the minterms. So here we can see that the combination of the variables a and b, since it's a SOP format of representation, so the first cell over here would just represent the minterms AB, something like this, as a bar b bar. So here you can see that in this particular cell the value of a is a and b, both are just zeros. So for an SOP format of representation, 0 means a complemented variable. Okay, So we can just write them down, or rather we can get a minterm for both the variables a, b, that should look something like this, as a bar, b bar. Okay, so following this particular convention, the other cell over here, that's cell number 1, should have a minterm combination that should look something like a bar b, where you can see the value of a is 0, so it's a complementary variable, whereas the value of b is 1, so this means that it's a non-complemented variable. So as I said, I repeat that in an SOP format of representation, a 0 always means a complementary variable, whereas a 1 represents a non-complementary variable. Okay, so if you would apply your head a little more, then you can get to see the the minterm combination for the cell numbers 2 and 3 respectively. So we can get another combination of minterm over here that should look something like a b bar, and for the cell number 3 it would be like a b, where both are non-complementary variables. Okay, so this is how the combinations occur inside a K-map. Okay, now if this expression was in the POS format, so like something like this, as we have seen over here. So let's just state it over here. If we had a expression that was in the POS format, so let's just write this down over here. Okay, if this was something like a bar b bar and then multiplied with a bar plus b, and then we had a plus b. So as you can see that this particular expression is in the POS format of representation. So it's a bit different. Now we can also see from this particular expression that it also consists of two variables, that is a and b. So the K-map would be a 4-celled K-map. Okay, so we would require a 4-celled K-map since the expression consists of only two variables, that's one is a and the other one is b. So if I just draw another K-map over here, that should consist of 2 rows and 2 columns, that is 4 cells. Okay, and then number up something this way, and let a represent the rows once again and b the columns, and then we number up the cells. Alright, there you go. So now for this particular K-map, since it represents POS quantities, where so each cell over here, contrary to the example that I just showed over here previously. So now the Karnaugh map that I'm just trying to display over here, it's each cell would just consist, or rather would just represent a particular combination of one of these max terms. Okay, so it's a little bit of a mistake over here. I'm just gonna rectify it for the moment. Okay, that's better. Okay, so we're back on our track. So now, as I said, each of the cells would just represent a combination of a particular max term. So the first cell over here, we can see that the value of a and b are both zeros. Now you should always keep in mind that whenever we have a POS form of expression over here, then here a 0 represents a non-complementary variable, whereas a 1 represents a complementary variable. Okay, you should always keep this in mind. So if we can take a look in the first cell over here, we can see that the value of both a and b are zeros, which means that the first cell would have a max term that would look something like, it basically represents a combination of max term, which would basically look something like a plus b. Okay, so because here both the values of a and b are zeros, and zeros represent non-complementary variable in terms of POS system. So the first cell is a max term that looks something like this. So similarly, the second cell over here, we see that the value of a is 0 and the value of b is 1. So this represents a plus b bar. So it'll have a max term that looks something like this. So similarly, the cell numbers 2 would have another max term that would be a bar plus b, and 3 would be would basically represent another max term that would just basically look something like a bar plus b bar, since both the values of a and b are 1s over here. So that's how each cell is designated with a max term in terms of POS system. Okay, so this, I mean, these are basically, two variable K-maps that I've just shown you for both the SOP and the POS systems. Now, if we were to basically, look at the extent of how big a Karnaugh map can get, then we can have a 3-variable Karnaugh map. If we have a 3-variable Karnaugh map, okay, I'm just going to show you one over here. Okay, so we can just basically represent the 3-variable K-map somewhat this way. I'm just going to show you over here. So there you go. Okay, we're going to draw a rectangular box this time. Now, since it's a 3-variable K-map, okay, so the number of variables is 3. So let's take, let's say for example, we assume that we have 3 variables A, B, and C that just makes up our expression which we are supposed to map in the K-map. Okay, so now in that case, the 3 variable, since the number of variables is n equals to 3, so the total number of cells would be 2 to the power n. That's 2 to the power 3 over here. That is 8. So we would basically require 2 rows, okay, and 4 columns in order to create a 8-cell K-map. Okay. So in that case, I'm just dividing it into 2 rows. There you go. And now we need 4 columns. So that's 1, and then 2, and then 3 and 4. Okay. So now since there are 3 variables, as we have assumed here, let's say they are A, B, and C. So let's just put A as the row element. Okay, so you can see that the row is supposed to have only 2 binary values. That's 0 and 1. Now here we have 4 columns. So in order to basically put the values of these columns, we need at least 2 binary variables. So the binary designations would be something like 0, 0, 0, 1, and then you just jump to the last one over here and then put 1, 0, and then come back again and put 1, 1. So that's how we just number them: 0, 0, 0, 1, and then 1, 0, and then come in the middle one, that's the third one, and then name it as 1, 1. So this is basically the convention of how you should basically number the rows and columns for a K-map. Okay, so as I said, let's just take A as the row element, and since we need 2 variables to designate the column, I mean the column values over here, so let's just put BC as the variables that just designate the columns. Okay, so this is how you can just basically create a 3-variable K-map where each of the cells over here, if this expression is an SOP expression, then each of these cells will just contain certain values. Now you can see that this first cell, now we can just basically number the cells over here. So just numbering them up. So 0, 1. Now again you go back to the last one, and then this is 2, and then this one's 3. Okay, and then again for the next row you do the same thing. So this will be 4, 5, and then 6, and finally over here you got 7. So this is how you can basically number these cells for a K-map that's greater, that contains greater number of columns, which is more than 2. Okay, so if the expression that we want to map over here, if it's an SOP expression, then each of these cells would contain certain combinations of minterms. So this first cell where you can see that the value of all the variables A, B, and C all are zeros over here. So if it's a minterm, then it'll be something like A bar, B bar, and C bar. So that's the combination of minterms for the first cell. And similarly for the second cell, you can see that, except C, both A and B are zeros, so they'll be represented in somewhat this manner: A bar, B bar, and C. So this is how you can basically represent, or rather just take up the cells as representing each of the minterm combinations when it comes to SOP system. Okay, but if you're working with the POS system, okay, I'm just going to clear them up for this explaining this concept over here. Just kind of hold on for a second. Okay, so as I said, if you are working with the POS system, then each of the cells over here, as I showed in the previous example, they would just basically designate, or rather represent, each max term combination. So here you can see that all A, B, C are zeros, so the first cell max term combination would look something like A plus B plus C, as zeros in POS represent non-complementary values. Now in the second cell you can see that except C, both A and B are zeros, so you just represent it as A plus B plus C bar, and so on. So that's how you just map a 3-variable K-map. Okay, so other than that, we can also have a 4-variable K-map, which I'm just going to show you over here. So that this one's going to be a 4-variable K-map. So you should always keep in mind that a K-map can be extended to maximum 6 variables. So you cannot extend a K-map beyond 6 variables. So that's the maximum limit. Okay, so that's the maximum limit of variables. Expressions that should include these number of variables, which can be reduced using a K-map. Okay, so we can basically reduce a maximum number of 6 variable expression using a K-map. Okay, so coming back to the 4-variable K-map representation. So since it's a 4-variable K-map, so we are going to need 2 to the power 4 number of cells, that is 16. So I need a bigger square over here. Alright, so that's a comparatively bigger square. Just pull the page down a bit. Okay. And so similarly, if the variables, let's say all the 4 variables be designated as A, B, C, and D, then in that case we will have basically, as I said, 16 cells. So we need 4 rows and 4 columns. So we're going to need number of rows should be 4, and the number of columns should also be 4. So in that case we need 4 rows, 1, 2, okay, there you go, 3 and 4. And then for the columns we need 1, there you go, 2, and then we got 3 and 4. So again, as we just number up the rows and columns over here, so similarly we're going to be doing the same. So the rows would be numbered in the binary fashion in somewhat this way: 0, 0, and then 0, 1, and then you got 1, 0 over here, and then you jump up to the 3rd row and just number it 1, 1. Similar to the way in which we numbered the columns in the case of a 3-variable K-map. Okay, and then if you just go to the columns and number them up, then that is quite similar to what we showed you in the 3-variable K-map. Okay, so there you go. And so since we are having 4 variables, so we can see that each of the rows need 2 variables to designate the value of each one, and that's similar to the columns. So we need 2 variables, that's AB for the rows, and of course CD to designate the values of the columns. So now each cell would be numbered in this way: 0, 1, then you could go 2 and 3, and then you need 4, 5, and then 6 and 7, and then you don't number the 3rd row. You just straight away jump to the 4th one and just start numbering from here on: 8, 9, 10, 11, and then come to the last remaining 3rd row and then number it as 12, 13, and this jump over here 14, and last one, that's the 3rd row, 3rd column, that's 15th. Okay, so that's how you number up a 4-variable K-map. And similar to the designations for SOP and POS systems, the variables would be just filled up in each of the cells over here. Okay, so these are the various different types of K-maps that I'm just given an intro on in this particular tutorial. So we're just going to be introducing you to how to use a K-map, or rather how to fill up a K-map in the forthcoming tutorial. So just keep watching.